Hello everybody. My name is Arkontis Politis. I'm from Tampere University, and we are ready to start the second session. The first part is actually the spotlights from the challenge tasks, and then there are a few regular papers too. So we start with task 1 and Annamaria.
I know you missed my face. So actually, I will not start with task 1. I just have like a very small introduction about the challenge and then the call for the next year. So one of the things that happened, let's say recently, is that we got this endorsement from the IEEE AASP, which is kind of like a renewing itself automatically. So it's a IEEE endorsed challenge now. We keep expanding, and I think that the main idea, we had so many tasks this year. We have different research topics, we have diverse setups in terms of machine learning tasks, and hopefully we continue doing some also tackling new research questions. Yeah, I just mentioned that we had a lot, so that a lot is 7 tasks, but actually there were more like 9 because some tasks had subtasks which were quite independent from each other. All the posters will be there for you to check in detail the one that you are interested in. In terms of participation statistics, we seem to have reached some sort of a balance that in the last few years there have been pretty much the same number of participants, but it's great. I mean, DCASE is going strong, so there's no worries about this. So I want to actually focus this introduction on the call, which is currently open for proposing tasks. And you probably are familiar with the idea that individual groups are organizing tasks. And we are asking people to submit 2 pages proposal containing details about the task. The name, coordinators, what is the definition, what is the research problem, and so on. So the deadline of this call is 13th of November. It's quite soon. We were hoping actually maybe to get some contacts before this workshop, but still you can, if you have some idea, you can come and talk with us. So I put here also the tentative schedule for next year to kind of have an idea of when you would have to work a lot if you are organizing a task. And practically that's for making the task description public and for releasing the development data set. And then a bigger part is after the submission deadline to evaluate and publish the results. I think this is, we were going pretty much with this schedule every year, so this is kind of the plan. It depends a bit on the workshop deadlines and so on, so we will align at least the later part with the workshop deadlines. But May, June, July, you can expect the end of it. So I think that one of the most important things I want to stress is that we want to help new people that want to propose tasks. So I'm one of the task coordinators, and Roman is here in the first, you know him, I'm sure. We want to help you, so if you have an idea, if you have this kind of half-baked idea, you can just come and talk with us. If you want some feedback on your proposal, send us a draft. It can be incomplete. It can be like, okay, what to put here in this data part to make it stronger, or what would be the best way of evaluating this, or what you think, just ask. We want to help. So, I mean, you know, just stop us and talk with us here at the workshop. That's the, yeah. Okay, now to the, what happened in the challenge. I'm also one of the organizers of the task 1, which is for low complexity acoustic scene classification. And that's already very classical task in the challenge, and it's for classifying audio recordings into scene classes. We have been making all sorts of changes throughout the years, from this kind of very basic setup to, okay, then we have more types of data, multiple devices, okay, low complexity. So the new thing this year was that we did a combined ranking. So we didn't look only at the accuracy or only at this or only at that, but we had a combination of performance, memory needs, and operations. So we did impose some limitations, but we made this kind of a weighted rank of everything. We did have plenty of submissions, so there is still some interest for it. And I put this table here to see kind of like the ranks are, okay, practically the best system in the challenge has, for example, in the max, quite low rank. There are others which are better in that side. But when you combine all the information, this came up first. So I think that this is quite an interesting thing, that the combined ranking has forced people to find a compromise, which of them to go more for. And the best performing system, actually, like in terms of accuracy, was not the one which is top ranked. Okay, it was from the same team, but that's a different story. But yeah. I think this is a kind of a novel element that we could still try to introduce maybe new things into for the future. Come and talk with us at the poster if you have also ideas on where to go with the acoustic scene classification task. And yeah, thank you.
My name is Kota Dohi from Hitachi, and the spotlight talk is on the design and motivation of our task. So anomalous sound detection is a task to determine if a machine is normal or anomalous from sound. We input some raw sound signal to the system. And the system outputs some binary predictions that represents the machine state. So we have been organizing the task for 4 years. And in the first year, our task was to detect anomalies without anomalous training data. So while normal sound data is easy to collect, anomalous sound data are rare, and it's very hard to cover all possible types of anomalies. In 2021 and 2, our main focus was on handling domain shift. So domain shifts are differences between differences in operational states or environment. And as you can see in this example, for example, for toy conveyor operating in a low speed can be subject to domain shift after its speed changes to a high speed. So because domain shifts can change the normal distribution of data and degrade the detection performance, handling of domain shifts plays an important role in development of ASD systems. So this year, our focus is on training a model without labeled test data. By labeled test data, I mean test data with normal and anomaly information. So for some machine types with enough labeled test data, we can leverage labeled test data for fine-tuning the model and improve the detection performance. However, this is usually not the case, especially for novel machine types. This is because for novel machine types, collection of labeled test data can take some time. Although the customers may want to deploy the SD systems very, very quickly, or they may want to start small, and they may want to start to see the effectiveness of our system in a small-sized experiment. In these cases, collecting enough amount of label test data and fine-tuning the hyperparameters using the test data is almost infeasible. That's why we came up with this kind of task. So we prepared two data sets. One is the development data set, which has machine types with label test data. And these machine types have already been used in previous tasks. And the other is the evaluation data set, which has machine types without labeled test data. And these machines are novel. Novel in a sense, these machines have not been used in a challenge in the previous years. So these are the number of audio clips in our data set. As you can see here, in the development data set, we had labeled audio clips, labeled test data, 200 labeled test data, while in the evaluation data set, we had unlabeled 200 audio clips. So I leave their results and discussion to my poster session, and please come and join us. Thank you.
Hi again. So the next task is the task of sound event localization and detection, evaluated in real spatial sound scenes. And for those of you that that are not familiar with previous iterations of the task, is basically a combined task of detecting temporal activations and classifying sound events of interest, but also at the same time finding the positions in terms of direction of arrival or actual position of the sound sources that produce them simultaneously. So it's a task that is a bit more preoccupied with the spatial understanding of the sound scene than just temporal and semantic understanding. The current iteration of the task is pretty much a continuation of last year's task 3, where for the first time we introduced a dataset of real sound scenes recorded with multiple human agents interacting with themselves and also with other sound sources in the sound scene. And all of these target sound events of interest were like temporally and spatially annotated. A little bit like you can see in that snapshot of a video from these recordings. And the biggest part of these recordings was used last year, but there were some important differences in this year's task. So, first of all, we extended the dataset with another 4 hours of these spatial recordings and their annotations. And this year we are also providing 360-degree video that is spatially and temporally aligned with the audio recordings. And the reason we did that this year is that we decided to introduce a new track in the task. So there is the track A that is in a way the traditional localization and detection task as we used to do it, using only audio information, only the audio recordings for the task. But we also introduced the track B, in which case the participants can use also video information. And a good question is why do we want to bring all that extra complicated baggage? I think the keynote by Andrew summarized it very nicely in the morning that it's very hard to get like spatially annotated data. So in a way, video is our best bet to scale this task to large data and generalize it, basically. So we wanted to promote that direction essentially. Another thing is that we included distance information. Before we had only directions of arrival for the sound events. This year we also included labels of actual distance of the sound sources, which is a tracking distance, meaning that if the sound source is moving, the distance is moving is also like the time variant distance from frame to frame. And the reason for that is that it's a rich queue, and there is quite a lot of interest lately in distance-dependent audio processing. I forgot to mention that task was co-organized by researchers in Tampere University and also Sony Research. And we have Kazuki here from Sony.
Okay, so this is the key, some key takeaway. So I think all systems support the CLD of multiple same class event from different directions. I mean, so there are some people talk that with the different direction. All systems tackle this problem of the overlap from the same class. And there are very little variety in the audio feature, such as spectrogram or interface difference and or novel loss function in this year. And yeah, no team currently use sound source distance information in any stage. So. Okay, and regarding the audio visual, so plenty of explanation with a video feature and feature engineering. And yeah, some video data augmentation is also used. Yeah, however, so only one team managed to do the better using video data with just audio only system. So I think so we need effective use video information for the sound event localization detection task is still an open question. Okay, so thank you for listening. So come to the poster and let's discuss about the result and discussion. Thank you.
Hi again. So I'm one of the co-organizers of Task 4, and at the poster, you'll get a chance to discuss with Francesco and Yannick, who you probably know if you've been participating to Task 4. I'm not reminding the task setup, well, for a matter of time. Plus, this is one of the oldest tasks in DCASE challenge. I'm just reminding here the novelties from this year. So if you were there yesterday, you have heard that since this year we made it mandatory to report the system footprint, both in terms of energy consumption and in terms of multiply accumulate. Another novelty is that we did provide separate ranking between single systems and ensemble systems. We had participants that were not quite happy about that, but I mean, we stand by this decision, and we believe that if we start monitoring system consumption, it makes sense also to try to move towards single systems, or at least have a differentiate analysis. And so, what is it to remember about this year? Well, the average, as pointed by Francesco yesterday, the average energy consumption has increased since last year. And the max energy consumption has increased too, so it's not only the average that is shifting. Also, one good news is that the top performing system is not the system with the largest footprint, and by far, which is a nice outcome. We also found that there are minor improvements with ensembling, at least at system level. If you are considering team submission, combining several systems, then ensembling does work. But if you are using one single system, then you can get 1 or 2% improvement. And the last thing is that it seems that we are kind of saturating on the task, and the performance improvement since last year. So for the previous year, we had usually a 5 to 10% improvement each year. So we started at 70% F1 score. Now we changed the metric, but we are around the 50-60% F1 score. But the performance improvement from one year to another was really marginal this year. So there is some sort of saturation in terms of performance. And so if you want to know more about that, please come and discuss with Yannick and Francesco at the poster.
Hi everyone, my name is Irene Martin. I'm from Tampere University, and I will be presenting this subtask. That this is the first year that we have introduced it. So this is also about sound event detection, but we have added these new labels, which we call soft labels, which it takes into account the uncertainty of the annotators. So we have created this Maestro real dataset, which considers 5 different acoustic scenes from real data, and the recordings are 3 minutes long, more or less. And then we annotated them using a weak label setup. This weak label considers a sliding window of 1 second, so we can get from this weak label a strong label annotation of 1 second resolution. And this is the data has been annotated with multiple opinions, so 5 annotators annotated each of these weak segments. And this is the data that has been used for the subtask 4B. So this year, since it was the first time, we don't have comparative, but we are happy that we at least received 7 teams submissions, and in total 22. And we use 4 different metrics to evaluate the systems, and we rank them with the highest optimum threshold F score. And we have seen that, given that the imbalance of the data, a lot of people were using different augmentation techniques, like mix-up or spec augmentation. And the best one actually merged the use of hard labels and the soft labels, because at the end it's true that we are evaluating it against the hard labels, but one of the rules was to use this soft label because we actually wanted to see how those benefit to the learning of the labels. So please come to the poster and then we can discuss what's going on with this task. So it was too simple or it was not interesting enough because we didn't get that many submissions. And what is actually the benefit in the use of these soft labels? And the last is, okay, we are promoting this soft label, but at the end we are evaluating with this hard label. So what it will be, how it will be more better way of evaluating this. So we use another different metric for it. So that's it. Thank you.
Hi everyone, this is Vincent Lostanlaine from CNRS, the French National Center for Scientific Research. I am here to present Task 5, Few-Shot Bioacoustic Event Detection. The author list is here, so I think Esther is here at the workshop, but aside from that, yeah, unfortunately, neither Ines, nor Borouge, nor Schubert, nor Dan Stowell is with us today. So this task began in 2020. With the intention of serving the needs of the bioacoustic community. It's a community which typically relies on template matching for their day-to-day applications. You know, they would scan a very long audio file, they don't know what's in it, and then they find something of interest, and they realize that it occurs repeatedly. And then the natural question that arises is, how often does it occur? How many events of this exact kind do I find in a very long recording? And that event type might not fall within a classification scenario in the sense that it might not be already present in an audio set taxonomy or a species classification taxonomy. So I like to present it as a tab completion for sound, if you will. You know, it's something that would sort of expedite your work. You've began the work, and then the machine carries on and follows accordingly. So we began in 2020 with various taxa of birds, some hyena sounds and meerkat sounds. And over the past 3 years, we've expanded the team. I'm also very proud to say that I think we are the challenge with the most women co-organizers in the team. So people from various labs who have contributed one or several sub-data sets of the following kind. As I said, we began with just birds and mammals, and now we have a zoo, an entire zoo of animal sounds, going from insects to marine mammals, the most recent additions being frogs and cow moos. So it's a very hard problem because it's a very diverse data set, and it's not at all clear how you could invent a machine learning system which, given the above, would generalize to the test set efficiently. We have evaluation metrics which are as classical as you can imagine. I will say a few more things tomorrow about those metrics, but yeah, they're typically precision and recall based. We have two baselines, template matching and prototypical networks, and we've had 6 technical reports. Here's the full list of submissions. Two things are worth noting. One is there is a strong domain shift, which I understand can be frustrating when you do really well on the validation set of the validation subset of development set. You might think that you're going to win, and then we report the results for evaluation, and suddenly, boom, it's not so great. All I can say is this is really a typical frustration that arises when working together between computer science and life science. The other thing to say, on a more positive note, is that we are far from saturation. This problem is far from solved, and it is an urgent need, it is a pressing need for biodiversity monitoring. So here are the F-score results. I won't comment on them, but you can find me at the poster for that. One last thing I will say is that together with the authors of the challenge and other authors, including Hao Liu, who was a participant, we wrote this paper to Ecological Informatics Journal called Learning to Detect an Animal Sound from 5 Examples, which is about how we can explain the task to a beginner or a newcomer to the field in 1 sentence. So I encourage you to read that paper if you're curious about our methodology. Thank you.
Okay, me again. Last time for today. I'm presenting audio captioning task. So the task 6A that works with the text retrieval task that is going to be presented by Wang, I think. So the idea is a task that has been running for the past 3 years, I think. The idea is that I have audio clips and I want to get a natural description of the audio clips. The news this year were that we introduced new contrastive metrics. So fence metric that was proposed in a paper in ICAS 2022, I guess. That is based on sentence BERT, and that is including like fluency error detection. So that was like the main aspect that we were interested in. Plus, there was this SPICE plus metric that is derived on SPICE, plus some correction on the parser. And that is based also on embedding comparison instead of just a distance between the parsed sentences. What we can see from this year is that we had this year a lot of audio extractors that were trained on audio text pair, like for example clap that many people have been talking about. And so these were actually used starting this year. We had like many different audio encoders where like previous year it was mainly PANs and everybody was using PANs. Now people are using like bits, or we've even seen people like relying on Whisper for audio encoding. We have 1 point progression in terms of spider metric, which was the ranking metric for the past years. So between 2022 and 2023, so the progression is rather slow in there. And one thing that did come as the side effect of the fluency metric in the ranking is that people did not fit the system on the cider metric, which they were doing previous year. Cider metric is not embedding like fluency, and so people like get away from this metric. And if you want to know a bit more about that, you can come and discuss with me at the poster.
Hello everyone, I'm Juan, and I'm going to give a brief introduction for the task 6B. So it's language-based audio retrieval. So this is the second year for this task, and we adopted the same task setup as previous year. So for the test dataset, we still use 1,000 audio caption pairs and use the mean average precision and the recall rate as the evaluation setup. And all the submitted systems are used to retrieve and sort audio clips according to their relevance to the text queries. And this year we have received 33 systems from 9 teams, and we have observed that all the systems have adopted bi-encode architectures and pre-trained audio and language encoders, and contrastive learning object for training system. Also, some external dataset used for system pre-training. And this year, the top 1 system has obtained a mean average precision of 0.4140, and which, in contrast to last year's top 1 system, which had mean average precision around 0.27. So you can see it improved a lot. So if you find it interesting, please come to our poster and have more discussion. Thank you.
Hello, my name is Mathieu Lagrange. On behalf of many people coming from all over the world, the poster has been made by Keisuke, so thanks to him also. I'm presenting the Foley-Sound synthesis task. Hopefully I will be able to switch. Okay, so the task overview, it's pretty simple. You have several categories. I differentiate roughly into event type like dog bark, footsteps, gunshots, and keyboard, and textualized sounds like moving motor vehicle, rain, and sneeze cough. The last one is a bit in between, and the difference between event and texture is always an interesting debate in terms of perceptions. We had 2 different tracks, with or without external sources for training, but we enforced people to identify their sources. We had many innovations for this task because it has been designed on the going. So we had a collab notebook including sound synthesis script given to the participants, and we run their code on our side to generate audio that we can evaluate. Okay, so it's a bit different from, let's say, Kaggle-like type of evaluation. So we had a 2-step evaluation because we strongly believe that human perception can be hardly put into numbers nowadays. Maybe at some point we will be able to do that, but we are far from that. Most of the community in generation rely only on fresh audio distance type of embedding like distributional distance. And we believe that it's a useful thing for designing tools, but for validating them it's not enough. So we had a 2-step approach where we start with objective evaluation and we compare the distribution of generated samples with respect to the evaluation set in a VGG space. We use the standard fresh audio distance, and we select the top 4 FAD systems per track. Top 4 means that we will be able to do the evaluation, the subjective evaluation, because we couldn't evaluate subjectively all the submissions. And we selected 20 representative audio samples from the sample that has been generated. Again, we need to prune down. That's the big problem when you deal with perceptions. Computer needs a lot of data, and humans, if you ask them to rate 2 billion samples, most of their answer won't be interesting. So we selected 20 representative audio samples using a really simple strategy, and then we moved on to the subjective evaluation. The innovation is that we asked to participants to rate, okay? But we didn't take into account their rate for the system they submitted. So we had 3 criteria: audio quality, fit to category, and diversity. Audio quality and fit to category has been evaluated by all the teams, all the members, whereas diversity has been holistically evaluated by the organizer. We ended up with some kind of balanced score. It's clearly can be improved, but we balanced less the diversity because it has been ranked only by the organizers using kind of a holistical procedure that can surely be improved. The outcome, we are at the DCASE workshop, and you could be wondering, this guy is talking about generation, what is going on? Because DCASE means detection and classification. In fact, ISMIR had the same problem because it's music information retrieval conference, right? And there is a lot of generation going on. They discussed about renaming ISMIR as music informatics research, and well, they said we are going to stick to music information retrieval and live with that. I hope that DCASE will allow us to live with that also. We are happy to have done the first perceptual evaluation also at DCASE and show that this is possible to run a subjective evaluation for challenges. And flashback to the first DCASE in 2013, where a glorious Emmanuel Benetos and Dan Stowell run the code of the system on Linux boxes. We did organizer-side code processing. 10 years have passed and Google Colab made things much easier, but still we had problems. Good participation for first edition, 36 systems, 17, and most are new to DCASE, even though the winner is a famous team from DCASE. Perceptual evaluation just really matters, and big thanks to Laurie Eller for allowing the task to do it well. She's really a specialist into that and put a lot of effort because it's really time involving. And big thanks to participants for allocating time for scoring. This clearly makes sense. It takes time, but it really matters. There's a lot of room for improvement if we are discussing about renewing the task. So please come to the poster and discuss. Thank you.
All right. So now I can move to some of the presentations of the regular papers. The next one is actually the authors could not make it here, Tanmay Kandelwal and Rohan Kumar Das, but they have sent a video. And there is their poster in the other room, just nobody there to discuss with you, but you can take a look. So let's watch the video.
Hello everyone, today I'll be presenting the paper Cross-Dimensional Interaction with Inverted Residual Triplet Attention for Low Complexity Sound Event Detection. This paper is being presented by Tanmay Khandelwal and Rohan Kumar Das at the DCASE 2023 workshop. It's a paper worked at Forte Media Singapore. We start with the motivation behind the paper. We know that sound event detection basically is classifying the different events with their particular onset and offset, and also classifying them into different classes. So we see on the right that the input audio after the sound event detection has been classified into various classes like speech, bird singing class with their onset and offset. Now, particularly for sound event detection, we see that the real world audio often contains a lot of overlapping sounds. Now, because of this, the state-of-the-art methods require high computational resources, which are not suitable or compatible with a lot of embedded systems. Now, one way is to go about reducing the parameters so that the model is actually compatible for the resource-limited systems. And it also further shortens the training time and the inference time. Now, one way to go about it is using the mechanisms like attention modules, which actually help in creating efficient low-complexity systems. Some attention modules actually add in computational overhead and actually end up ignoring the spatial and channel interdependence. Thus, we feel that there's a need to introduce a novel, low-complexity attention module, which helps in sound event detection. Now, for this, we take inspiration from the MobileNet V2, which from that, we propose to incorporate an inverted residual network with a linear bottleneck architecture to replace the standard 2D convolution. So we see the architecture on the right-hand side. We introduce the attention module, which is taken as an introduction of the triplet attention module into the IRN network, which actually adds up a negligible computational overhead. Further, it also helps in learning the cross-dimensional interaction. Now, this attention module on the right-hand side actually consists of 3 branches, each of which is actually captures the spatial and channel dimensions, the interaction between the spatial and channel dimension. Now we see the outcome from this report. We see that the baseline, which stands at 0.351 and 552, has around 1.1 million parameters. Once we introduce the IRN network to replace the standard 2D convolution, the parameter size reduced down to 301K. After adding the SE attention module, which is the squeeze and excitation attention module, we see that there's an improvement in the score, but the number of parameters increased quite a lot. A similar trend is seen after adding the coordinate attention module. But when we add in the proposed module, which is the triplet attention module, we see that the score actually improved, but similarly, at the same time, there's a negligible increase in the parameter size from 301K to 304K. Further, after adding the data augmentation technique, as mentioned in our paper, using the external set provided by the challenge itself, adding in the interpolation consistency technique, and also adding 2 methods for the post-processing, the median filtering and the probability correction, we see an improvement of the score, which actually ends up improving the baseline by 34.1% through this cross-dimensional interaction and the methods proposed here. We see that this system actually ends up only using 27.6% of the baseline parameters, seeing a decrease from 1.1 million parameters to 304K parameters. We further perform another ablation study to see the gain of each branch in the triplet attention module. So here we see the interplay between different branches. So and then the aggregate weight is taken. So only 1 branch, then 2 branches, then 3 branches. We see that the final branch interaction between FT, CT, and CF actually ends up performing better than all the 3. And it has around the similar number of parameters, 304K. We also give a comparison with the top ranked systems of the last year's challenge. We see that the proposed actually stands on 2nd position on the validation set with only 304K parameters compared to the 15.4 million parameters. And our scores are better than the top, the 3 teams beneath us. So we see that our system is actually able to perform quite better than the baseline, as well as comes in the state-of-the-art systems. That's it. Thank you.
Right, and next. Is this one right? Yeah, it's okay.
Hello, everyone. My name is Haohe Liu from the University of Surrey CVSP. I'm super excited to present our works on Foley sound synthesis, especially for this year's task 7. And unfortunately, the first author of this article is not being here in the DCASE challenge. So I'm doing this presentation on his behalf. So a quick recap of this task. So we can look at the image on the right-hand side. So the input to the system is basically a category of sound, such as the dog bark. And our system will, based on the input labels, synthesize a sound effect. So that's a bit overview, pretty simple. So there are a few issues on previous studies. So for example, the general quality is still an issue. So it's not as realistic as expected. And the second issue is that the model generation can have very varied quality. So sometimes it generates good samples, sometimes generate bad samples. And another issue is about the data hungry, because the model is data driven. So you need a large amount of data to enable the model to get a sense of the overall distribution. So we address these 3 issues in our proposed system. So to address the quality issues, we switched the baseline method to the state-of-the-art audio ODM method. So the audio ODM is basically audio generation model based on listen diffusions. So we will come back to this later. And second improvement is we propose an automatic sample selection method, which we use a clef model to calculate the clef score to do some initial filtering on the sample quality. And for the data hungry issues, we try to resort to the transfer learning strategies. So we pre-train our models on large scale of data set and then fine-tuned on the official training data set. And another thing to note is we condition our model based on both the clap audio encoder and the clap text encoders, but we use audio during training and text during inference. So we find this is pretty useful because we can utilize large amount of unlabeled audio data during the pre-training stage. And yeah, this slide shows the result of our system. So we did pretty a lot of arbitration studies based on different tricks, such as using the pre-training or not, or if we use the one hot vector as condition or use the test embedding as conditions, or if we perform the filtering or not. So it's have pretty detailed result. And it's quite surprising to find the scaling up of the models is not always help. Like this row and the last row, this row is about small models, this row is about large models, and small models even perform better on some kind of the sound. Yeah, and we can listen to a few demos. So the first few is the baseline sound. That's dog barking and gunshot and footstep sound and motor vehicles. So here we come to our proposed model. This dog barking sound, this gunshot sound, and footstep sound, moving vehicle sound. Yeah. Our model is fully open source on GitHub. So if you're interested, please feel free to play with our models. And the main takeaway here is audio ODM is a pretty useful architecture. And there is a team in this year's DCASE Task 7. They simply use our open source model without any fine tunings and even achieve the 4th place in this task. So I think it's pretty promising. And if you have any other things to discuss, please feel free to come to our poster session at P220. Yeah, thank you very much.
Hi, I'm Yuna Lee and I'm from AI to XL Lab in the Institute of Convergence Technology, KT Corporation in Korea. I'm here to present our research, Future of Bioacoustic Detection, Boosting with Fine-Tuning Strategy using Negative-Based Prototypical Learning. The following research is based on the work I did with my colleagues on the DCASE 2023 Challenge Task 5. Task 5, to simply recap, the task 5 is to detect certain sound events on audio files in bioacoustic domains such as animal vocalizations. 5 samples are provided in the beginning of the file, and we have to detect the same features in the rest of the file. As can be seen from the term few shot, provided audio segments are rare and have a variety of duration. This year, 2 datasets that do not overlap with the training set was added to the evaluation set. Because of this, we had to implement a framework that could perform robustly across multiple bioacoustic domains. For this challenge, we analyzed the bioacoustic training dataset, and we found out that in this task, the ratio between positive audio features and negative audio features is higher unbalanced. When we visualized the ratio between 2 classes in TSNE embeddings, we were able to get these figures. The red denotes positive features and the blue denotes negative features. Further, we also found out that the general prototypical loss function can cluster positive class but lacks to cluster negative classes. As it may lead to severe overfitting on the positive events of the training set, we thought that the sole training on the prototypical learning framework was insufficient. Based on this analysis, we applied 2 additional learning frameworks in our method. First, we combined contrastive learning and the prototypical learning frameworks on the training session. By doing this, we were able to make the most out of positive data in the training set. Second, to better identify the 5 positive samples given in each audio file of the validation set, we had an additional fine-tuning session. During this fine-tuning session, we applied our novel loss function, negative prototypical loss function. Based on this loss, we cluster negative classes by minimizing the distance between negative prototype and negative features, while maximizing the distance between negative features and the positive prototype, thereby widening the gap between 2 classes for more robust performances on the evaluation set. Based on our framework, we extracted TSNE embedding from the same audio file. This time, the network was done training after fine-tuning session. The following TSNE figures tells that our method was able to cluster negative classes densely, thereby dividing positive and negative classes better than general prototypical learning framework. Through our method, we could achieve F measure of 81.67 on the validation set. Additionally, when we added a transductive inference method, our method was able to increase the F measure up to 83.08. Our method ranked 5th in the DCASE 2023 Challenge Task 5. This concludes the presentation. For more details, please visit our poster, which is 21, during the session. Thank you for listening.
Hello everyone, my name is Paul and I'm a PhD student at Johannes Kepler University in Linz, Austria. In this presentation I will show you our efforts to improve a natural language-based audio retrieval system with the patch-out fast spectrogram transformer and large audio captioning datasets. So natural language-based audio retrieval systems are essentially like search engines for audio recordings. They take a textual query as input and they retrieve the most relevant audio recordings from a database. Most of these systems are based on the dual encoder approach, which use 2 separate encoders to project audios and textual descriptions into a shared audio description space in which matching audio description pairs are close to each other. And then classification, tagging, or retrieval can be done based on similarities or distances in this shared audio description space. In our case, we used pre-trained audio and language models, and we trained them using the NT cross-entropy loss. On large audio captioning datasets, we used the default Clotho dataset that comes with task 6b, and we also used audio caps and wave caps. In our experiments, we compared a range of different audio embedding models. On the left-hand side here on this figure, you can see different audio embedding models and their corresponding performance measured in terms of mean average precision, which basically measures the rank of the correct audio recording among the top 10 results, and is correlated to the rank of the correct audio. So as you can see, the patch-out spectrogram transformer performs generally better compared to the CNN10 and CNN14 convolutional neural networks. The difference between the past versions is the way that patches are extracted from the input spectrogram. So past S uses overlapping patches, and past S extracts past N extracts non-overlapping patches. And the difference between past L and past S is that it's shallower, so it only uses 7 instead of 12 self-attention layers. The results for different language models is given on the right-hand side. There you can see that, in general, those language models that are larger perform better. We also tried to improve the retrieval performance with a new augmentation technique that we call GPT augmentation. The idea behind this was that the recordings in the Clotho dataset, they are associated with some keywords or tags, and we wanted to include those keywords in the caption. So what we did is we essentially prompted ChatGPT and asked it to rephrase a caption and also include the keywords. On the left-hand side here, you can see the query that we used to prompt GPT. In blue is the original caption, and in orange are the keywords. On the right-hand side are the rephrase captions, which are semantically very close to the original one, but now they also include the keywords. Okay, let's see some results with this. So we did an ablation study where we basically trained the system with and without GPT augmentation. As you can see here, the improvements were only marginally or marginal. So the improvement was around 0.5 percentage points, and I assume that this is because each caption in Clotho is, or each audio in Clotho is already associated with 5 different captions. So by doing this GPT augmentation, the variety of captions is not increased by a lot. We also compared our results to the DCASE baseline and the current state of the art. So the figure here, or the Y range of this figure here is cut off. But in general, our system performed better compared to the baseline and also better to the current state of the art. Thank you for your attention. If you have any questions, visit my poster.
Wow, I have never chaired a session that was early on time before. Great, let's thank our presenters again, and then we can move to the posters for more discussion.